Hi everyone, and welcome back. In this lesson, 14.3, we're going to look at apportionment methods. So apportionment just is dividing things up, but it's finding a method to divide things in a fair manner. So this occurs, in governing bodies, and also, if you're looking at like a city or a precinct and you need to determine how many police officers will be divided up and stationed in certain precincts, we need to look at fair ways of doing this. There's four methods that we're going to look at, and those are Hamilton's method, Jefferson's method, Webster's method, and Adams' method. Again, these four methods are used for apportionment. You don't want to confuse them with the four voting methods that we talked about in 14.1. Okay, so plurality, board account, plurality with elimination, and pairwise comparison are four methods used for voting. These are methods that we are used for apportionment. Before we look at some apportionment methods, we need to talk about some important words. Like one of them is the standard divisor and the standard quota. So the standard divisor is just when you take the total population under consideration and you divide by the number of items to be allocated. Okay. We use that standard divisor to then figure out the standard quota for a particular group, and that's determined by dividing the population of the group by the standard divisor. So once you find the standard divisor, you then use that to figure out the standard quota. Here's an example. A problem facing Orlando Centricare, a healthcare provider that operates 5 medical clinics, has recently hired 60 doctors. Since the clinics do not all serve the same number of patients, the organization decides to apportion or divide up the 60 doctors based on the number of patients who visit each clinic in a given week. Okay, and there's our table. So in Clinic A, there's 246 patients a week. In Clinic D, there's 211, and so on. So there's a total of 1,080 patients per week. So if Clinic A, if we were to divide this up, we would take 246 divided by 1,080, so 22 and 7/9% of the doctors should go there. Now, we know that you can't have 7/9 of a doctor, so we need to apportion the doctors so that each clinic receives its fair allotment. Okay, so we're going to determine the standard quotas for clinics B, C, D, and E, and then we're going to talk about the different methods we can use to apportion. So what we need to do is first find the standard divisor. And we know that to find the standard divisor, it's just going to be the total population, which in this case is 1,080, and we're going to divide by the 60 doctors because we are dividing those up among the different clinics. And when we divide 1,080 by 60, we get a nice number, 18. Okay, so that number we're going to use to find our standard quota. So the standard quota is that we're going to take the population that clinic serves. So let's say Clinic A, for instance, that would be 246, and we're going to divide by the standard divisor 18. And 246 divided by 18 gives us 13.67, as you can see there. So that's how they're getting the standard quota. Okay, we're going to do that for all the clinics. So this was Clinic A. For Clinic B, we're going to take 201 and divide that by 18. For Clinic C, it's going to be 196 divided by 18. For Clinic D, it's going to be 211 divided by 18. And for Clinic E, it's going to be 226 divided by 18. And when you do this, you should get 11 0.17 for clinic B for its standard quota. For clinic C, it's going to be 10.89. For clinic D, it's 11.72. And clinic E is 12.56. Okay. What I would like you to do is take a second and add up those 5 numbers. Do you get 1080? Okay, the answer is, I'm sorry, do you get 60? Okay, we should be getting 60, not 1080. Do you get 60 for your answer? And the answer is no. Okay, we unfortunately get 60.01. So that poses a problem because we have 60 doctors. We don't have 0.01 of a doctor. So what we need to do in order to use one of the methods, we need to look at what's called the lower quota and the upper quota. So the lower quota is the standard quota rounded down to the nearest integer. So for instance, in clinic A, my standard quota was 13.67. So its lower quota would be 13. The upper quota is the standard quota rounded up to the nearest integer. So I would round up to 14 for the upper quota. Okay. So the lower quota and upper quotas for clinic B would be what? So clinic B, the lower quota would be 11 and the upper quota would be 12. Conventional rounding of standard quotas can be a problem though because we can end up with more than what we need. Okay, so 61 doctors instead of 60, for example. So this is where those 4 apportionment methods come in. So let's talk about the first method, which is Hamilton's method. This is the easiest one to mathematically apply, okay? So to use Hamilton's method, I have the procedure right there, which you can follow along. The first thing we need to do is calculate the standard divisor for the set of data, and we already did that, right? So from the last problem, if you'll recall, my standard divisor was 18, okay? Then we need to calculate each group's standard quota. So we're gonna make a little chart here. So I'm gonna have clinic, and then my clinic is A, B, C, D, E, and then we'll have a column for total. Okay, and under clinic, we're gonna have patients, so the number of patients each clinic serves. We're gonna have our standard quota, and then underneath that, what we're going to need is the lower quota. So for Hamilton's method, we're gonna round each standard quota down, okay? And that is the lower quota. And then we've got a final row for Hamilton's apportionment. So using that method, how many doctors will be assigned to each clinic? Okay, so patients we can just copy from the above table. And if you'll remember, we had 1,080 patients to serve. Okay, we also figured out the standard quota. So we're just going to copy that line over again. Okay, remember that gave us 60.01. Okay, so again, those first 2 columns came from our original table. We took each of the patients and divided by 18, and that gave us these numbers. And when we added it, we didn't get 60 exactly, which is what we do need. So we're going to use Hamilton's method. We're going to find the lower quota. So I'm going to take each of these standard quotas, and I'm just going to round down to the nearest integer. So this would be 13, 11, 10, 11, 12. And if you add those 5 numbers up, you get 57. So now we have another problem. The problem is we've got 3 remaining doctors, and we need to figure out where they go. So what happens is this 4th step here, we're going to distribute any of the leftovers to the groups with the largest fractional parts until all the parts are distributed. So when we say fractional parts, we're looking at the numbers after the decimal. Okay, so here I've got 0.67, 0.17, 0.89, 0.72, and 0.56. So the leftovers are going to go to the groups with the largest fractional parts. So the largest number is 0.89, and then the next largest would be 0.72, and then 0.67. So those are where the 3 leftovers are going to go. So I'm going to add one more doctor to Clinic A, and they're going to now have 14. Clinic B is going to stay 11. I'm going to add one more to Clinic C, so that will become 11. I'm going to add one more to Clinic D, that will become 12. And then Clinic E is going to stay 12. And now when you add that up, you'll get exactly 60. So using Hamilton's method, Clinic A is going to have 14 doctors assigned to them. Clinic B will have 11. Clinic C will have 11. D will have 12. And E will have 12. And now we have exactly 60. Okay, now you may see a problem with that where it might be unfair in certain instances. And that's what we're going to discuss in 14.4. Just like with the voting methods, the apportionment methods have some flaws as well. Okay, you can try this next problem on your own. Okay, and I also see that I am missing a portion of my notes here, so bear with me while I pull up the newer document. I guess this would be a good time to use the restroom if you would like. All right, now it should be good. Okay, bear with me. Close your eyes if this makes you dizzy. Okay, here we go. Apportionment methods. So I asked you all to do this problem on your own. Okay, here we go. So now we're back in order. We have, so both of the examples, the one I did and then the one you could have completed, satisfied what we call the quota rule, which says an apportionment for every group under consideration should always be either the upper or the lower quota. Okay, so not every one of these methods uses the lower quota. Just Hamilton's solely uses the lower quota. So now we're going to look at Jefferson's method. Okay, next. So one of the weaknesses that can occur using Hamilton's method is that the groups that receive the upper quota get an advantage over the groups that use the lower quota. So Jefferson's method uses a modified divisor, and the modified divisor is a divisor that approximates the standard divisor. So instead of getting a standard quota, we obtain what we call a modified quota. It's basically the same thing though, just a different name, okay? And the way we get that is just by dividing the group's population by the modified divisor. So same process, but it's modified this time. Okay, so here's a procedure, and we're going to work out this problem here. So this is a good way to check your answers from the last problem where you had this republic and you had to figure out use Hamilton's method to apportion the 250 legislature seats among the 5 states in that republic. So we're going to do that here, except we're going to use Jefferson's method this time. And again, in Jefferson's method, we're finding a modified divisor, okay? And we're going to take the modified divisor to find the modified lower quotas, and then apportion to each group its modified lower quota. Okay. So if you'll recall, using Hamilton's method from the last problem, we found, or you should have found, the standard divisor should have equaled 35,200, okay? So what we're going to do is we're going to round down to the nearest integer for Jefferson's method. So for Jefferson's, the standard divisor, which we call a modified divisor, is going to be 35,000. Okay, so we're taking 35,200 and rounding down to the nearest integer. Okay, so I'm going to recopy from the problem that you all did on your own. All of this was given, okay, the population. So here, 1,003,200, and so on. And the total population was 8,800,000. Okay, I'm also going to take what you should have gotten for your standard quota when we used Hamilton's method. So remember, what you should have done was taken the population, for instance, right here, 1,003,200, and divided by 35,200. And then these are the values you would have gotten. So this is using Hamilton's method. Okay, so for the modified, since we're dealing with Jefferson's, now we're going to be taking our population and we're going to be dividing by 35,000, the modified divisor. So here you divide it by 35,200. Here you're going to divide the population by 35,000. Okay, so you should get this. Okay, and now we're going to find the modified lower quota. So it's very similar to Hamilton's. We're rounding down now. We're just using the modified quota to round down. So we would get 28, 35, 142, 23, and 21. Okay, and if you add those up, you get 249. So we should be getting 250, right? So it's less than the number of available seats. So now what do we do? So if the sum of the modified lower quotas is too low, as it was in this case, we want to use the lower modified divisor. And if the sum of the modified lower quotas is too high, which it was not in this case, you would use the higher modified divisor. So we're going to try this again. Okay, so what we mean by that is 35,000 was basically too high of a divisor for us to use. So instead, we're going to try like 34,900 instead. Okay, maybe I'll get rid of that. I'll put that here. Okay, so what we're going to do now is we're going to divide by 34,900. So a little less than the modified divisor that we used. So now we're going to take each of the populations, we're going to divide by 34,900. Okay, and you'll get the following. By the way, feel free to pause the video and try getting these values on your own. And then you can just check with me. Okay, and now we're going to do the same thing. We're going to round down to the lowest integer. And now if we add all those values, we get 250, which is the exact number of seats that we needed. So with Jefferson's method, there involves some trial and error. If you look online, there are some calculators that you can use. You would type in like Jefferson apportionment calculator, and there are calculators that you can use kind of like Excel spreadsheets so that it's much easier to play around with the divisors there rather than use a calculator and type in these numbers 5 times until you get the right one. Sometimes it'll come down to like a thousandth of a number, so it can be tough to figure out the divisor that will get you to the exact number. Okay, so it is trial and error with those. Okay, if you need to take a break, feel free to pause the video because we still have a little bit to do. We need to talk about 2 more methods, Webster's and Adams. So in Webster's method, we're going to round the modified quotas to the nearest integer such that the rounding gives the exact sum to be proportioned. Okay. So to give you an example, again, we're going to take that same problem, and I just recopied the values we got. So the standard quota, so you could see. What we're going to do to get the modified quota is we're going to choose a number that is less than, greater than, or it could even be equal to the standard divisor. So remember, the standard divisor we had gotten was 35,200. And when we divided each of those populations by 35,200, we obtained those apportionments. Okay, but remember, we fell short. So if we round standard quotas to the nearest integer, it ends up being too high. Okay, too high means that we want to use a larger divisor. If it's too low, we want to use a smaller divisor. Okay, so we use the standard divisor of 35,200. So since it was too high, if we divide by a higher number, we'll get a smaller quotient. So that's the whole theory behind it. So let's try dividing by 35,250. Okay, and again, I'm picking a higher number, slightly higher, because when I add up the numbers, it comes out to 251, which is too high, using 35,200. Okay. All right. So what we're going to do is we're going to divide by 35,250. Okay, let's try that. Okay. So if I take 1,003,200 and divide by 35,250, I end up with 28.46. So notice when you divide by a higher number, you will your quotient will be smaller, and that's what we want, because when we totaled it, it came out to 261, and that's too high. Okay, so we'll increase our divisor. So here we get 34.85 That's 141.58, 23.06, and 21.69. Okay, and we're going to, in this case, round, let's see. So here it tells us to apportion each group its modified rounded quota. Okay, so what we're gonna do is round using this number here. So 4 is less than 5, right? So if it's 5 or more, you round up. If it's 4 or less, you leave it alone. So here that's going to be just 28. This 8 will make the 4 go up to a 5, so that's going to be 35. This 5 will make the 1 go up to 2, so that's 142. That's going to stay 23. That's going to go up to 22 because of the 6. And now if you add up those numbers, you actually get 250, which is what we wanted. Okay, so that's Webster's method. So one of the things we need to pay attention to is whether or not these apportion methods satisfy the quota rule, because they need to satisfy the quota rule. Okay, so do you think all 3 of the apportion methods discussed so far satisfy the quota rule? Why or why not? So pause the video and try to think about that. Okay, if you answered no, you are correct. Jefferson's method can violate the quota rule because you're using a modified quota, right? And Hamilton and Webster's, they don't necessarily violate the quota rule, but they can still have flaws. Okay, and some experts agree that Webster's is the best method, but it is time consuming. Okay, so the last apportionment method is Adams' method. It was named after John Quincy Adams, and he proposed a method that's completely opposite of Jefferson's method. Instead of using a modified lower quota, as Jefferson proposed, Adams suggested using a modified upper quota. Okay, so again, we're going to take the same example, and I just recopied the first 2 rows there because they didn't change. And just remember that we got those values there by dividing by the standard divisor, which was 35,200. Okay, so using Adams' method, we want to determine a modified divisor such that when each group's modified quota is rounded up to the nearest integer, the total of the integers is the exact number of items to be apportioned. We'll refer to the modified quotas that are rounded up as modified upper quotas. All right, so instead of dividing by 35,200, let's raise our divisor, increase it a little bit. Let's try 35,400. Okay, again, this is trial and error. So I'm going to take this top row here and just divide it by 35,400. And you can pause the video, see if you get the same numbers. I'm getting 28.34, 34.71, 140.98, 22.97, and 21.60. And for Adams' method, we're going to find the modified upper quotas. So now we're going to round up to the next integer. So that's going to be 29, 35, 141, 23, and 22. And if you add those 5 numbers, you get exactly 250, which is what you want. Okay. So in some cases, you may need to use a decimal number as the modified divisor, like I was saying. So for example, if you have a divisor of 34, that might be too small. and 35 might be too large, so you may need to try 34.5 or 34.05 or something that will give you the exact number of items to be apportioned. Okay, that's the goal. Again, you can find calculators of these online. Please feel free to use those because it does save some time. Okay, but you do need to know what to put into, the calculator to make it work. So as long as you have some idea of what the standard divisor or modified divisor will be, you'll be okay. Okay, and you can try this problem here. So this problem is using all four of the apportionment methods. It'll give you good practice to kind of go back and recall what were the different methods that we used and what did we do with them. So that is the end of the video. I also have a summary here, so feel free to look at that. And also pay attention to what each method favors, because that will help you think about any potential flaws that each of these methods has. All right, enjoy your day, everyone.